proposed by Nathan Mars, who's considered the inventor of this particular concept. And he did it maybe while he was working at Twitter. And it's part of the book, Big Data Principles and Best Practices of Scalable Real-Time Data Systems, co-authored with Jim Warren. Would suggest everybody to have a look at that book. The main feature of a Lambda pipeline is a dual processing approach. So there is a batch layer and stream processing layer, and we'll get to all these pieces, Lambda, Kappa, and Delta, in the future slides. But at a high level, there are three different pieces. There is a batch layer, there's a speed layer, and there's a serving layer. And dual processing happens for both batch and stream. The batch layer, you can think of maybe any Hadoop or Spark processing framework, which computes accurate but high latency results. For a speed layer, maybe Kafka or Flink, which provides low latency approximate result. And the serving layer merges both the outputs for queries. So this is a good pipeline. This used to be a good pipeline, which was needed for running complex analytics along with some historical context. Then came the Kappa architecture. So this was designed in LinkedIn by Jay Krebs, and it's a stream-first approach, treating all data as streams. So there's only a single processing pathway. Everything is treated as stream. All data is considered as stream and processed in real time. So it's an immutable data storage. So any new change which happens on the pipeline has to be a new file, and the changes have to be reprocessed. So the complexity is a bit high. If there is any bug in the file and some of the older data needs to be backfilled, then because of the immutable data storage, the files have to be reprocessed. And it has a lower code path. Use cases mainly for Kappa is any kind of real-time analytics where batch layer is not really necessary, like log processing, monitoring system. Yeah. Then came the Delta architecture. So Delta, proposed by Databricks, based on Delta Lake, sometimes also called as Medallion. We'll discuss it down the line. It merges both streaming and batch into one single pipeline using Delta Lake format, and it provides ACID guarantee. So it's a unified storage and processing layer with no distinction between batch and stream. It's a single pipeline with structured streaming and batch on the Delta Lake, and it enforces schema, supports schema evolution, and it can also guarantee some timetable capability. So some of the tools using this would be Delta Lake on Databricks, Spark. Yeah.
Nilanjan, I just want to interrupt for a second. I was misinformed about the length of your time. You do have 45 minutes, so you're good until 11:30 Eastern time. So,
thank you.
Okay.
Okay. Coming to the deep dive of the Lambda architecture. So as we discussed, Lambda architecture is a overall data processing architecture designed to handle large data volumes in high velocity by taking advantage of both batch and real-time pipeline. And the three key pieces over here is one batch layer, one speed layer, and then we have the serving layer. So the batch layer processes all data periodically to create a master data set or main data set and recompute the result. Like the main characteristic of the batch layer is an immutable data store. So any data has to be processed, if reprocessed, if there are any changes or bugs identified. It does provide accurate, comprehensive result, but the latency can be high, sometimes minutes and up to an hour. Speed layer, on the other hand, can process data in real time and provides low latency updates for those results, and is generally used to handle data just arrived after the last batch arrived. It provides fast but possibly approximate results for any kind of analytics or partial results. It's not complete. So that's why we have the serving layer, which merges both. It merges result from batch as well as speed to provide a unified view. For batch, generally we use tools like Hadoop, Spark, and Flink in batch mode. For speed layer, we can use Storm, Kafka streams. There are multiple different options available. We had Samza, then Flink. For the serving layer, we can combine both these pieces, maybe using HBase, Druid, Cassandra. There are multiple offerings on that level as well. Why did we need Lambda architecture? So that is the question which we need to go over next. And what are the main advantages and disadvantages, if any, which caused new future architectures to grow? Like, why did we need Lambda? Why did we get bored of Lambda? Why did we come to Kappa and Delta eventually? So at a high level, the data gets ingested and gets sent to both. The batch layer is basically for a full-scale processing. The speed layer is for real-time processing. The batch layer processes data and updates the main view or the master view periodically. The speed layer processes all the incoming data immediately and update the results in near real time. The serving layer merges outputs from both layers to serve the queries. The main few advantages which we have with that architecture is it provides good fault tolerance and high scalability. It combines accuracy from batch and low latency results from real time or the speed layer. So it can handle both historical as well as real-time data. Now, batch layer does ensure eventual consistency for correct historical result. And we do have some fault tolerance. We can reprocess data if it occurs anytime. And this pipeline can handle heavy volume, petabytes of data or more. The main complexity or the disadvantages which this pipeline has is mainly two different code paths. So as we see, there is a batch layer and a speed layer, and both needs to be maintained. So there's an operational overhead, separate cost for storage and processing, and this logic duplication. So same logic needs to be implemented on two different systems for batch and speed. And it's pretty complex to do that. Dual code bases, maintenance overhead, all this. And there can be data duplication as well if the raw data is stored in both layers. So to address all the drawbacks or the challenges with Lambda, there was improvement in this architecture and move to Kappa, which is basically a single layer or a stream first approach. So at Kappa, everything is a stream. And so basically it's a pipeline design, where everything is a stream and there is no use for a separate batch and streaming pipeline. It does process everything as one single stream processing layer, something like Kafka or Flink. Like unlike Lambda, where we have two, we have just one unified pipeline over here. It does create immutable event log. So that's the source of truth for the Kappa piece. And data is stored as an append-only log. So if there are any changes, because events are never modified. So corrections, if needed, like if any of the business logic change, if we need to reprocess some of the older files, we need to reprocess. So corrections are handled only by reprocessing. Although it does provide the reprocessing capability for historical data analysis, so that particular point can be both an advantage and a disadvantage. So it does help us avoid two separate code bases. Like we don't have that maintenance overhead, but then need to be a separate processing overhead if we need to recalculate any of the older business logic. Some of the teams do consider a batch layer in Kappa, which is basically a slower stream processing, but there's no separate infrastructure needed. So the events or the kind of use cases where this would where this would be useful is any kind of an IoT application, any transaction log processing, which is basically written down as a durable log to maybe Kafka. There's a stream processor, let's say Flink or Spark streaming, which does consume the log and applies some transformation and then outputs the result to some downstream application, maybe like a real-time dashboard or some kind of downstream database. And as we can see, one of the use case, which was pretty well described by Uber, was they do maintain a couple-like pipe or couple-like architecture to process all the events in real time and then reprocess those events at the end of the ride for any kind of billing adjustment. I would like to take a minute to discuss the advantages and disadvantages of this architecture as well. So starting off with the advantages, this is simpler than Labra, no maintenance of two pipelines, so simpler to maintain, but it has a higher dependency on the streaming tech or the infra. So there would be strong dependency on Kafka Flink. That experience will be needed because if you want to do just real time, everything processed as stream versus so-called batch, which would be a slower stream, there'd be a strong dependency on Kafka and Flink. Advantage, it would have all real-time and historical data in one system, but the reprocessing can be slow because if the data set grows large, we have to do, and the data set is immutable, so you have to do reprocessing of the from point in time. It has easier maintenance because of the single code base, which we have over here, but this is, as you understand, it's not suited for any kind of batch analytics like monthly reports. For that, we need to go back to Lambda. There were some inherent challenges with Kappa over here. So we moved on to a improvement approach, or this was a new term coined by Databricks called data. Some may also call it medallion. So in the Delta architecture, basically, we get some levels of improvement from Kappa. Delta architecture is basically similar, a very similar data design pattern or data pipeline design pattern, which is used to organize data logically. So the goal is to incrementally and progressively improve the quality and the structure of the data as it passes through a medallion layer. So we have the levels in the medallion naming convention. As you can see on the left, there are batch sources, streaming sources, generating data, pushing all the raw data in the raw format in what we call a bronze layer. Their bronze layer is just a landing zone for the data with no schema necessary, no transformation being done at the bronze layer. And then the data moves into silver layer, where we define the structure, enforce the schema, do all kinds of transformation on the bronze level. And that's actually where the majority of heavy volume of transformations do happen. And at the gold layer, we create curated small data set, which is fit for each custom specific business use case. Like it is, there would be specific data set for any kind of metric or KPI we are tracking, which will be used to update some dashboard, or maybe some data which is consumed daily for any kind of ML training, any kind of DSML use case downstream. So going back, as the data enters the bronze layer maintains, like basically ingests and maintains the data in the original format. The data gets appended and grows incrementally over time. It is not supposed, there should not be any transformation at the bronze layer. It is just a landing zone. So without any transformation, it helps us in any kind of deep processing or auditing for any historical data if any changes are identified, because all transformations are done at the silver layer. So there are quite a few steps performed at the silver layer. Like we do any kind of data validation, deduplication, consistency checking. Like some of the tools like Databricks and Snowflake does offer capability to identify what kind of data, like if there was any schema change, so we can have schema validation, schema enforcement over here. There is some defined storage format on how we can store the data, like most fields in terms of something new which has come up, variant or binary to protect against any kind of unexpected schema change. Metadata columns might be added, modified in this particular silver layer. We also, while building the silver layer, we ensure that there should be always at least one non-validated and non-aggregated representation of each record. So if there is any aggregate representation of any downstream workload, those representations should be applied or should be created at the silver layer, but sometimes they're done in the gold layer too. So we do data cleaning, validation, deduplication, normalization here, and we improve the data quality from the bronze layer by correcting all the errors, inconsistencies, and things like that. We structure the data in a more consumable format for downstream processing. And how we enforce data quality is by schema enforcement, handling on null values, missing values, data deduplication, resolution of any out of order or late arriving data issues, if any, data quality checks, enforcement of those quality checks, ensuring schema evolution, typecasting, and lastly, if needed, joins between multiple such bronze assets to create the right silver asset. At the gold layer, gold is a pretty powerful layer and can be considered as the pinnacle of this whole Delta architecture. And that's all the downstream applications depend or derive the data from. So at the gold layer, basically, that's where we do the power analytics. It can serve self-serve, BI, and ML. It has highly defined views that do drive all the downstream analytics dashboards, and it's highly aggregated and filtered. But a few challenges for each of the layer which we can discuss. What would be the processing or reprocessing overhead for each of the layer? Like for bronze, one of the major advantages is since we are not doing any transformation, any issues or bugs identified in the data can be reprocessed easily in the silver layer because it's just a landing zone and it provides append-only lock. For silver layer, transformation logic might have some overhead because we are processing the data, doing some transformation, and any change in that business logic, schema evolution can be handled natively, but any kind of changes in business logic will require some change in that particular code. Gold is a single source of truth for any downstream ML, BI, DS use cases. So there needs to, and it has a pretty strong schema binding. So if there are any changes needed in those gold tables, the column needs to be added, dropped, modified, new gold table needs to be created. That's a separate maintenance overhead. So although we improve data quality along the way, so does the overhead for maintenance and some of the complexity in performing any kind of code change. But despite all the pointers we discussed, why did Kappa fail and why did Delta win? So Kappa, let's take an example. Like if we want to do fraud analytics and any kind of fintech data set, let's say streaming fraud analytics, and we want to get alerts in real time. While doing that, we want to backfill 3 months of corrupted data due to a schema bug or any kind of schema error. While doing that, we need to prove or ensure data lineage for compliance. So in Kappa architecture, basically replaying 3 months of streams is pretty costly and error prone. So we don't have any transactional control over the corrections and no historical versions for compliance audit. But in Delta, we can use merge. Basically, it's a good functionality in tools like Snowflake. So merge can fix corrupted data. We have time travel capability, which can rerun reports at any point in time in the past date. And since we have a unified access for analytics and streaming ML model, we can perform, we can govern, or we can ensure governance each step of the way while we do both backfill as well as real-time stream. With that context, let's move on to how data reliability changed over time. And then we'll come and discuss how data reliability and observability is critical with the three architectures. So traditionally, we had robust file systems, maybe I would say pre-2010, which was very easy to set up, which had low cost. There was no schema enforcement, no lineage versioning. It was prone to manual errors. And then came the whole batch ETL data warehousing process where we had structured ETL pipelines, better analytics capability, but it did have latency, sometimes daily, sometimes hourly, and it was brittle to a schema change. So it was not dynamic. And it had limited visibility. So that's why we filtered down a warehouse to a lake or a mesh to fulfill each use case. And we also discussed the Lambda and the cup architecture, which came after that, which had a lower latency, like it did provide stream-based inside, and it had separate concerns for both batch and stream, but it did have a complex architecture. It was hard to reprocess data. It had poor data consistency guarantee. Then came the Delta architecture, where and then we started getting into Lakehouse post 2019 onwards, which unified batch and stream. It did provide ACID guarantee and ACID compliant transaction. It did have time travel and schema enforcement, strong data governance capability, but due to the majority of the providers offering, like Snowflake, Databricks, there is open source version of it as well. We do have Medallion can be implemented anywhere, but that since the term was coined by Databricks, we are going by that example. So we do have Iceberg, Hoodie, which is open source. Those are Apache projects, but what we're mostly familiar with is Delta, which is an offering from Databricks. It does have a slightly higher storage cost or compute cost, and there's vendor lock-in cost as well for egress for any kind of data to be moved out for any organizational use case. Very recently, we have heard few terms about data observability and data contracts. So let's say 2023 onwards. And during that period, we are trying to identify or we are trying to learn how proactive error detection can be done. So how data SLAs and lineage can be established, how automated testing and alerts can be set up, or basically telemetry each step of the way to identify data issue as soon as it happens, or maybe predict in some case if we, in the future, we can have some agentic workflows to do that. And we can perform a complete shift left on the data quality. So those are the few areas which we'd like to, where we are right now and we'd like to move toward. Although this does have some operational overhead, and this would be a very critical, complex DevOps on top of the data pipeline. But yeah, we would like to get there. Moving on. So let's discuss data observability next. In data observability, we do have 5 core pillars. And that's what all the industry leaders talk about, where the main pillars of data observability involves data freshness, which ensures if the data is up to date. So freshness refers basically to how fresh is the data. Did the table update today? Like in real time, did the data from the most recent events that come in? So having access to the most fresh data, the freshest data, is critical in any kind of business use case, like let's say in sales, lead scoring or personalization. We're trying to buy something off Amazon and it did not get you the most latest information of the cart. The data doesn't really make sense if it's showing the data from, let's say, a week back. So freshness or being up to date is highly critical. Data volume. Volume basically tracks or monitors the data flow and consistency. So the expected amount of data which is supposed to flow daily, if that is flowing in without any kind of sudden spike or drop. And going back to freshness, there are a few key metrics which we can track, like lag. If the What's the difference between the processing time and the event time? And if there are any late arriving data. So some of the tools which we can use to track data freshness is Kafka consumer lag monitoring. We can also have some watermarking capability on Flink or Spark. For volume, we are processing the overall data flow and consistency. So basically we can check if there are any kind of missing alert or missing event alert or any kind of expected volume versus actual. If we have some, and there are some of the tools which do provide email-based models which just predict how much the data volume can come in, and there's an automated alerting mechanism if the volumes differ. So for this, we can perform some kind of idempotency checks and statistical baselining based on the historical data. We also do check the data schema. For data schema, we have to detect any kind of schema changes if it was not previously notified. So how the data is structured, what kind of data type it's using. It can be as major as maybe changing the format altogether. You're getting the data as Parquet till yesterday. As of now, you started getting XML or CSV altogether. Versus a minor change, a column which has been added or maybe deleted, or a data type for one of the columns change from varchar to string or maybe into float. So those kind of schema changes or evolution, deletion, any kind of schema modification basically. So that needs to be detected, be identified and reported to have a proper observability pipeline. We also check lineage. So we need to track the data movement from source to use, or basically source end to end. So does it give you the visibility on where the data comes from, how it is transformed, and where exactly it's getting used? Complete visibility from source to end. Data quality is last but not least most critical piece, which also data quality and distribution, I would say both can be combined into one single point. So ensuring accuracy and completeness of the data. So AI models sometimes work better over here where we have complete data set, then they can provide the right correct training. So there shouldn't be any kind of data leak or data loss, to summarize. We do have found a lot of issues, and we do find a lot of issues day to day where a lot of data, late arriving data, missing data, we do classify them as missing data, and then we identify those late arriving. So those needs to be solved as a part of this as well. Doing this, we identify a lot of other issues like key metrics we can use to track this, any kind of duplicate record or out of order events, end-to-end pipeline delay, where at which stage, how long did it take? So for duplicate, we can have a deduplication. We can use Kafka idempotent producers. We can track out of order events by watermarking, like on Flink. For end-to-end pipeline delay, we can do distributed tracing, any kind of OTel tools. So OpenTelemetry does provide a detailed description on this. And we can also track back pressure alerts, like any kind of Kafka and Flink metrics, like CPU, queue depth, things like that. Before going to reliability, let's take another minute to see why data observability is very, very critical, despite whichever data pipeline architecture you choose. So data observability is very critical to any data team for success. Like bad data doesn't just mean bad insight. I mean, it obviously means that, but other than that, it can also mean some wasted resource, wasted compute, a lot of cost, or basically bad reputation for anybody depending on the data or any downstream team using it. So it does cause a lot of lost reputation, lost revenue, anything you can think of, all bad. The important issue is who or which team does it affect the most on when it's identified. So it's identified early then it does affect the data engineering team. The lower, or if it's affected, if it's identified later in the stage, it can affect all the business stakeholders, external customers, and maybe even general public, depending on what layer the issue is originating and who has access to it. So to enable data trust at scale, we have to do a lot of data testing and need to address some of the basic problems that appear within the data preemptively. So we have to start off with small teams and then scale to bigger, and then make an enterprise-wide pilot or POC to roll it out to all the other teams. To accelerate any kind of such operational efficiency that follows scalability, and I mean, data trust is critical. So data observability doesn't just accelerate the creation and maintenance of those monitoring metrics which we are doing, but also provide the automatic lineage. So using the quality metrics will be enforcing the quality metrics, which will help. So it's kind of a symbiotic relationship between the observability, logs, metrics, and tracing whatever data point we can generate, which fulfills the DevOps as well as the data part of the same pipeline. And it does get or does grant good time to value. So it does deliver immediate time to value. So this would be a great differentiator between any kind of traditional data quality practice and a comprehensive data quality practice with good quality checks involved. I do have linked in the link over here, data observability value calculator. So this particular deck will be shared post the presentation, where you can go to this link and quantify how much, what's the value or what's the exact value of your data observability. Like, what is the data downtime you can afford? What number of incidents you have faced, maybe in the last 6 months, 3 months, 1 year? What was the time to detection? What was the time to resolution? And based off all this, what's the exact number or dollar lost or impacted? So that's how you measure success for the data quality practice. And it's as critical, quantifying these numbers is as critical as the tool we choose or the tool we use. So a simple calculation can be estimated for the estimated number of incidents you have, let's say, per year. Whether you're currently catching them or not doesn't matter, by dividing the number of tables you have in your production by 15. And the reason and the description is all listed in the calculator. It's a very good and niche tool. Yeah. So do have a look. Moving on to reliability next. So reliability engineering focus on building systems, basically, which deliver data consistently, accurately, and with minimal delay. So any kind of stream or near real time. Or this logic does apply to micro batch pipelines as well. So even under high load, schema changes or failure scenarios, it can provide consistent, accurate data. So the core principles involve, for sure, obviously, fault tolerance, which is designed for failures, like any kind of node or network outage should be resilient against that. We can have some kind of replication in Kafka. For example, if we talk about tools, for Kafka, you can use replication. For Flink, we can do checkpointing, and we can handle do backpressure handling. We also need to have data durability implemented. For that, we should need to ensure there is no loss or corruption of the data. So in Kafka and Flink, we can do exactly once processing. That do help. Need to have immutable logs and idempotent sinks. The third principle is observability. We already discussed observability. So monitoring and detecting any issues as fast as possible, as early in the pipeline before it gets to the downstream business users. So tracking throughput, latency, error rate, automating alerts for each step of the way, what kind of tracing we can establish along the way will be helpful. And then scalability. So whenever the load arises, whatever scalable mechanism we're implementing, what kind of auto scaling we're implementing. So the scale up factor, the scale out factor has to be pretty high and designed, obviously, as per budget. It's obviously advisable to have very high scale out factor, nav factor, but might not be permitted by the IT team, or in most cases, the budget board be enough. So we have to do it smartly. Horizontal scaling, obviously, by doing Kafka partition, Flint tasks, and we need to also have resource isolation. So to summarize, the main challenges which we can face is data loss, which we solve by replication and checkpointing. In Kafka, we can have acknowledge x equal to all or Flink save points. The challenge over there is there will be some trade-off. It will have higher latency versus durability. And secondly, for the smoke processing issues, we can have dynamic scaling and back pressure handling, like enabling auto scaling in Kafka and throttling on Flink. Sorry, for Flink scaling and Kafka throttling. But in this case as well, we need to monitor Kafka consumer max pull records to avoid any kind of out of memory issues and things like that. We can also have duplicate data. So for duplicate data, we can do idempotent writes or deduplication. We can use Kafka message IDs or any kind of tools like, or any kind of data structure like Bloom filters. We can test idempotency and duplicate event injection to solve this, or there can be custom tooling in my transformation part. If I do have schema breakage, I can maintain a schema registry, but then again, I can enable the schema evolution over time. You can use tools like Confluence Schema Registry. So the best practice for any kind of a good, robust, reliable pipeline is to test rigorously, like have a proper chaos engineering framework. Something which I'm really fond of is what Netflix uses, Chaos Monkey, but modified for your custom use case. Defined SLOs and SLAs, like what does 4.9 mean? What does 5.9 mean? How do we arrive at that number? What is the business impact of my downtime? For that,
Nilanjan,
yes.
I don't mean to interrupt. I know you're wrapping up right now, but we are at time. We won't have time for questions, but I want to make sure that Jack Smith, our next speaker, has his kind of full time here. He's got reinventing MDM. So he's going to talk about that with the context of AI. So we're going to do a quick change here. Do you have just one closing sentence you want to add, or?
Sure. Sorry, I got that. Lost track of time. Yeah, to summarize, reliability engineering, and there are key practices and considerations which we can make. It would be detailed, described, and I will add notes to the deck, which I'll send later. But thank you for listening in.
All right. Well, thank you.